No problem. So when we look at this problem in general, all right, we know we're going to be looking at phases. So we know that phase is equal to 2 pi times delta L over lambda. We know that for constructive interference, that's going to equal to 2n times pi, right? And then for destructive interference, phi destructive, that will be equal to 2n. So with the odd case, m can equal 0, and that makes sense. It's when you have 0 here, it doesn't really make sense. But right, because half wavelength is certainly a physical length. So we want to make that small correction. It's amazing. Okay, and so this is sort of what we have in our starting point. So let's read the problem again and see what we have and what we don't have and how we want to start it. Okay, so two speakers, again, we can see the speakers here, are separated by this distance d1. And we have here this distance from the one ear to one of the speakers, d2. All right, so we want to assume, it says the amplitudes of the sound waves from the speakers are approximately the same. Fine. It gives you a number for d2. And we want to consider the full audible range for normal human hearing. So this problem is going to want you to do the same thing many times. We're just going to set it up to do so to the point where doing that thing is trivial. All right, so it says, what is the lowest frequency that gives minimum signal? So that's destructive interference in the listener's ear. Okay, so that's A, and that's the first thing we're going to do. And then you'll notice that I think B, C, and E until you get to lowest frequency that gives the maximum signal, right? So then you get D, E, and F. So they want a sort of 6 different frequencies, but we're just going to do the first 2 because I think, as you'll see, once you have the expression for the first 2, or for parts A and parts D, the other parts that follow are trivial. Okay, and that should make sense. So if we're going to pick destructive, and I think you'll notice when I wasn't feeling well, I sort of just jumped to the first thing that came to mind without thinking about it. But we have to do a few things first. First, we have to pick whether we're constructive or destructive. The problem very clearly states that we're looking at destructive interference, at least for parts A, B, and C. Right? So we have we want to start with phi equals 2m plus 1, right? Pi. So we know that, where m is just, do you want me to, I can go back and forth between m and n. I'll use n so we can be self-consistent. There's no reason. It's a dummy variable, so it doesn't really matter. But I'll be consistent with my notes at the very least. I can do that. Okay, does everyone see why I picked this value of phi here, the destructive value for phi?
Yes.
There's a bit to unpack. I want to be sure everyone sees why I made that choice and then what the consequence of that choice was. Okay?
That's perfect.
All right, good. So we put phi, we set it equal to what we have here, right? Which is that we can set that equal to 2 pi times delta L over lambda. Okay, but there's 2 things we have to keep note of here. So first of all, delta L we don't really have yet, right? because remember, the delta L is the path length difference between the two speakers to the ear. I want to draw it like this because you can see that that other red line is delta 2, but they meet here at the ear. All right? So in order to find this length, we can just use our Pythagorean theorem, and we get that it's the square root of d1 squared plus d2 squared. Right? You just know that from our right triangles and stuff like that. So delta L, if we're going to call this D2, we'll call that D1. Yeah, Mina.
Professor, can you elaborate a little bit more about the distance that we took the hypotenuse of this triangle? Because I know in the rubric itself, it's not very clear.
In which, in the problem?
Yeah.
Okay. So this is one of those cases where they provide you a picture because the picture sort of makes everything very easy, right? So you have the D1, it tells you is that there's two speakers separated by that distance. So that's your D1 here. This is just two speakers separated by that distance, right?
Right.
And then in front of one of the other speakers, right directly in front of this speaker here, you have you're some distance away from it. So that's D2. So now, where this could be confusing is that delta L is equal to L2 minus L1, but this is not L1, right? You could say that this is L2 for the path length, and this is L1, if you'd like, but this is not L1. So we have to construct a triangle, right? We have a right triangle here, and knowing these two sides, knowing D1, this separation between the two speakers, and knowing L2 lets us figure out from the Pythagorean theorem the hypotenuse of this distance L1, right?
Oh,
and then we can do,
Mm-hmm.
and then we can do the path, and then when we do the path length difference is L2 minus L1, we can write that as equal to D2 minus the square root of D1 squared plus D2 squared. Okay? So now all of a sudden, good. So now all of a sudden we have delta L in terms of stuff we know, and we can plug that in here. But before we do that, I'm going to leave it as delta L for now, just knowing what it is here because it's more compact. But you notice it's asking us for frequencies. So what I wrote before I had to take our abrupt break, was that the velocity of a wave, and we're dealing with sound waves, right? So the velocity we know will be 343 meters per second. Yeah, and if you get a negative number for the distance, you can just flip them around without losing generality. You shouldn't get a negative. I guess you might. No, because, no, you will get a negative because it's the hypotenuse is always bigger than L2. So if you want to get the positive number, you can just flip it around and say, oh, well, it's the larger distance minus the smaller distance. That would be fine as well. So you're not really losing generality there. In fact, I'll flip it even because that's going to make more sense. We should know from our triangle inequality that this will be the greater quality or quantity, right? So that makes, I didn't even think about it, but that makes sense. So V equals lambda F, and then we have that 1 over lambda, which we have in our equation here. 1 over lambda will be equal to F over V, right? So we actually want, so we can rewrite this whole thing coming back to the phase as 2n plus 1. We can cancel out these pi's. Times, or will equal 2 times delta L. I'm just going to keep it as delta L for now. and that will be times the frequency over the velocity, right? And so what I can do here is I can solve for this frequency, because this is the frequency for destructive interference, and you'll notice, I'll point out the result at the end. We can see here that F equals, it's going to be a big fraction, 2n plus 1 times V over 2 times delta L, which will be, I'll write it here, the square root of d1 squared plus d2 squared minus d2. All right, that's our path length difference. And you'll notice now that we have the frequency in terms of, what you call it. Yeah, I mean, yeah.
Professor, sorry. Is L2 delta L is L2 minus L1, right? Why did we reverse
L2 minus L1. So I'm just recognizing that it's sort of arbitrary which one is L2 and L1. So I'm going to only because it's hard to erase. Because I recognized that this is actually going to be longer, I'm going to just call this L2. And that's just recognizing because a student quite correctly got that the original way I had it would give you a negative number, and you can just make it a positive number because it's a displacement. You're just looking for a magnitude there. But I was thinking about it, and I realized that in the triangle, you're always going to take the longer. You can prove mathematically that the hypotenuse will always be longer than one of the legs, right? So it makes sense to call that L2 and this one L1, and then subtract those.
All right, got it. Thank you, Professor.
Okay, yeah. So now we have our frequency, and we can see that our lowest frequency for destructive interference will be the lowest value of n, right? So the lowest value of n we can have is 0. So if we, and that the lowest value of n we can have while keeping everything, a number, because zero, when you have a frequency of 0, it's sort of doesn't make a lot of sense. And it's not going to be useful for this course. And you'll notice that we want to go between 20 hertz and 200 kilohertz, so we don't want to consider frequencies in the problem below 20 hertz. So we can put this n equals to 0, though, and still get 1 here, right? Because 0 plus 1 is 1. And you can plug in your velocity for the speed of sound. You have d1s and d2s here. It's just a little bit inconvenient. And then you get your 2. So you can calculate from the given information this frequency. And then for parts B and C, right, you just look at this for n equals 1 and n equals 2. And then you've got your 3 lowest frequencies for destructive interference. Now, what if, the question I have is, how would you set this up for constructive interference? And I would want you to try this. I normally, if this weren't going onto YouTube, right, I would want you to work on this for about 10 or 15 minutes. But try working on it for 5 minutes and see if you can set it up on your own. And think about this step. This is the main setup step. I'm going to change colors and circle it in blue and yellow. All right? How is this step changing when we look at constructive interference instead of destructive interference? Yeah, Mina.
Professor, sorry. I kind of got lost of where what integer we're gonna be used for value n or m.
So for n, so for when you have something like 2n pi, right? When it's even, you're not going to start at 0. You're going to start at 1, 2. So for even values, you'll start at n equals 1. They'll just be natural numbers.
All right.
But for odd, for 2n plus 1, when you have something like 2n plus 1 times pi, here you are going to start at 0, so that you get 1/2, 3/2, 5/2, and so on. Okay? So here, in this context, n will equal 0 1, 2, and so forth.
Okay, and for the sub question is essentially 0. Start with that.
Right, right. So for A, it's 0. For part B, you plug in the number 1 here, and then find the new frequency. And then for the part C, you plug in n equals 2, and you get the next one.
Got it. All right. Thank you, Professor.
Professor,
Okay.
sorry, I was also lost. Like, so what should I put the value of v velocity? I didn't get it, so
Very good question. Very good question. So when we're looking at this, you know, do you remember in Physics 1 how you'd often assume your gravity was near Earth, so you'd use g equals 9.8 meters per second, right?
Yep.
And they'd never say that in the problem. Well, here they're going to say, assume the amplitude of sound waves from speakers are approximately the same, blah, blah, blah. The important part is you assume that it's sound waves on the surface of the Earth in standard temperature and pressure. So the velocity of that, just like we know g is 9.8 meters per second, that velocity is going to be 343 meters per second. Okay? Good question.
Okay.
It's one of those things that's implicitly given, right? It's not explicitly given.
Professor, can you type the value on the chat room?
Hmm?
Can you type
Oh,
the
type
value?
the value in the chat room? Yeah.
Would be great. Thank you.
Sure. Speed of sound in air is 343 meters per second. And I'll even type it here because the chat room won't come up on YouTube. So I can type it oh, there's too many E's there. At STP, which is standard temperature and pressure, is 343 meters per second. Okay?
Perfect. Thank you, Professor.
Yeah, you're welcome. So yeah.
I have one question more, right? I mean,
Sure.
so for D, we have to solve by putting the value of phi is equals to 2 n phi, right? And do the same, but the value of n must be start from 1, right? That's what you said.
Right. You basically you got it. Yeah. You just switch this to you just switch this part here.
Mm-hmm.
Oh, hold on. Oh, it's wanting me to type. You just switch this part here to 2n pi, right?
Yep.
And you have to start the value of n at 1 instead of 0. You got that. And then yeah, you just set it equal to 2 pi delta L over lambda. The pi's will cancel again.
Oh,
And you solve. If you solve for f. Yeah, very good.
thank you.
It's exactly what you do.
Thank you.
Okay? You're welcome. All right, since we seem to have that, I'll just go over it quickly. Again, this will be on YouTube, so I'm going to delete this. So it shouldn't be too bad. But to change that first step from 2n plus 1 to just, oh, it's not, the pencil's not there. We get 2n, right? Yellow's a terrible color, I'm finding. I'm going to switch colors. It's not as effective as I think it is. We'll go with red again. So we have 2n pi equals 2 pi delta L over lambda. But this time, the 2 and the pi, they cancel. And if we can say that this is equal to delta L, I don't have these things memorized. F equals V, so 1 over lambda is going to equal F over V. Yeah. So it's going to be times the frequency over the velocity. And then from here, you should be able to solve for F. F equals NV over delta L. And that should do it, right? Using all the same stuff we did last time. So that should give you the frequencies, minimum frequencies for constructive interference. Okay?
Yes.
All right. So let's move on. So we're going to talk about intensity and sound level. So this is an important thing. Intensity is the power over the area. This will be a very useful relationship as we go in. This should be intuitive though, right? When you look at the intensity in terms of the density and the frequency and all that stuff, that might not sound, you know, that lets you break it up into sort of chunks that you can look at. But the power over area should make sense, right? If you're listening to a speaker and you move farther away from it, does it get louder or does the volume increase or decrease, basically?
Decrease.
Right. And I think you can all imagine that, right? If something's loud, to get away from it, you go farther away from the source. Pretty simple. But intensity is a product or is a property of pretty much every wave. Take light, for example. Intensity, instead of being volume, would be brightness, right? So like a laser is brighter than your lights that you have on your ceiling, your room lights, right? You can look at the light for your room, and it's not comfortable, but you're not going to hurt yourself. Whereas if you have a laser, you shine it in your eye, or you look at the sun, you're not going to do very well. That's not going to be good for you. The intensity is too high. So an easy way to look at it is its power over the area. And you can relate the intensity to the amplitude of the wave with this formula here. Now, a lot of times when looking at intensity, of a spherical wave, we use the surface area of a sphere, which is 4 pi r squared. And this will give you your sort of very basic intensity calculations, all right, when you're from a source. As you can see, this tracks with what you think. As r increases, as r goes to infinity, I goes to 0, right? You can clearly see that. Sound levels, this is what I wanted to get to. So sound levels are often measured in decibels. You've probably heard this before, like a jet engine is 130 decibels. The threshold of pain is 120, rock concerts, 110, conversation. And whenever you're in a conversation about hearing, or whether a source of sound is too loud, or it's the volume of a sound, what it should be, you'll often hear it in terms of decibels. And decibels are related to intensity. Now, the intensities that we're dealing with are the intensity you hear relative to the threshold of human hearing, all right? And you'll notice that the threshold of human hearing is very small in watts over meters, and fundamental, power over meters, 10 to the minus 12. So this is called the threshold of human hearing. And at that point, I is equal to I0. The logarithm of 1 is 0. So, you're fine there. But you'll notice that for every factor of 10 increase in intensity, 10 decibels is added to the sound level. All right? So basically, if you want to figure out how loud something is, you just figure out its intensity in decibels. You figure out its intensity in watts per meter squared. Take the ratio of that to the threshold of human hearing, take the logarithm of it, multiply it by 10 dB, and then you get your intensity level. Okay, pretty straightforward stuff. Nothing really overly complicated about that. I want to talk slightly, sort of nicely, about sources of musical sound. You'll notice that the geometry of the sound changes whether you have two ends opened or one end open, right? So you'll notice when you look at harmonics or fundamental harmonics, you have this quarter wavelength here, and the wavelength is 4 times the length of the tube. And you'll notice as you get up in those harmonics, right, the frequency here is equal to V over lambda, or NV over 4L. And then as you increase N, you can get those harmonic frequencies until you get up here at 7. The wavelength is 4L over 7, or as you can see, it now fits inside the tube, whereas before, at the fundamental frequency, the wavelength is actually 4 times the length of the tube. And you'll notice that you have a similar function here, but it's half, right? It's NV over 2L. Now, some interesting things occur to give you these formulas. So you can derive these formulas from applying what in differential equations you would call boundary conditions, right? And I want you to notice that when you have a closed part here, you have what's called a node, right? From those standing waves, you have a place of 0 oscillation. And you'll notice that whenever you have an open cavity, you always have an antinode. All right? So that dictates, so if you have an antinode here and an antinode here, this smallest difference you could have here is a wavelength, right? Because this must be an antinode, this must be an antinode. The distance between an antinode is a wavelength. So you naturally get that. Now here, in the one open end, the distance between, shortest distance in waves between one antinode and then the very adjacent, the very next, one node and one antinode. A node is just where there's no oscillation, right? It's these little 0 parts here. Okay, that's a node, node, node. I hope that it's making sense when I say node. And then antinodes here is going to be a quarter of a wavelength. So this makes sense. We use these boundary conditions, and we can figure out how waves must propagate through the cavity. All right, because they have to be that way. The boundaries are sort of insistent upon it. Okay. So let me draw it. Yeah, Amina.
Professor, I'm sorry. I have a question regarding intensity. So definition for intensity, right, is the time rate of energy transfer, which is power, over the area of surface intercepting the sound.
Well,
so yes.
So it's sort of, I think you're right with that area part. It's the area of the, because as you get away from it, as your sphere increases, it'll have an increasing surface area, right? So at a distance, you will have some spherical surface area. So if you're 5 meters away from the source, then you have to consider a sphere with a surface area of 4 pi times, I said 5 meters, right? 5 squared. So that's the area that goes there. It's the area of the sphere when you're that distance away from the sound. Because the sound doesn't just go in a straight line. You can't get all of it in one direction. It disperses spherically. Why can an elephant hear so well? That is a good question. Its threshold of hearing, it probably depends. Hearing fundamentally works on vibrating membranes in your ear. So elephants may have a more finer tuned membrane that picks up with a lower threshold of hearing. So then they might be able to hear it or have it be affected by sounds from farther away. Right? So they would have a lower threshold of hearing. Yeah.
So Professor, just to make sure I understood correctly, the sphere you're talking about, its diameter is actually the distance of our ear to the source of the sound. Is that correct?
It's the distance from the ear. So let me draw a picture. Sure. Hold on. I can only do one at a time, everybody. So if you have a sound source, right? And say this is you listening here. So the sound doesn't just go right to you and nowhere else, right? Someone over here will hear the sound as well by the Wiley sign, right? So as the sphere goes, and I'll represent it with concentric circles, but it's a sphere, but it'll grow sort of bigger and bigger, and then when it gets to you, you'll hear it, right? So you'll hear it at an intensity, and then you'll be some distance. So it's the diameter of the sphere, you'll notice, or the radius of the sphere, not the diameter, right? Because the diameter would be twice as big, and the sound disperses through the sphere. So when you're this distance away, the intensity is going to be equal to the power at the source, right? This output power.
Yes.
Over the intensity at the point you're at will be that output power divided by the surface area of the sphere at which you hear at.
Got it. And the radius is actually our distance from the source of the of the sound. Got it. All right. Thank you, Professor.
Yeah. Good. You're welcome. Before I get to the last question, Royesh asked about an antinode, and I want to answer that question. So I'm going to delete this because that's a really important question. So when we have a standing wave, right, which we talked about briefly yesterday, let me draw one here. Okay, so in a node, so in a standing wave, you have these lobes, right? And in the lobes, so in these parts of the lobes, the string moves very rapidly up and down. But you'll notice there are these sections where the string doesn't move at all, right? So the section where the string doesn't move at all are called nodes, right? There's no movement there. You're just sort of sitting there. And an antinode is this area here. This would be an antinode. And that's where the string is moving maximally, right? So that's where you're moving the maximum up and down here. That's an antinode because it's moving the most, and that's a node because it's moving the least. It barely moves at all. Okay? And so what we're essentially looking at in this but max and mins of what is important. You need the context, right? So it's maximum displacement of the string. And here it would be of the sound wave, right? So we're sort of looking at these as standing waves in these tubes. And we have the boundary conditions that say that at a closed end, right, whenever we have a closed end, we need to have a node. So an area like this where the sound isn't moving. And whenever we have an open end, we must have an antinode, all right? Like this, where the sound wave would be oscillating the most rapidly. Or if it were a wave on a string, the string would be oscillating the most rapidly. Okay? Okay, good. There was another question. I can't remember who asked it. It popped up while I was answering Mina's question. I want to be sure we get to everyone's questions because they're pretty good questions. Okay, well, if you remember, just pop on in. I wanted to talk about these sources of musical sound. Music can be very interesting because you know, brass instruments, wood instruments like saxophones, clarinets, trumpets, a lot of their sound depends on the geometry of the cavities within them. And in fact, you change notes by changing the sounds, or by changing the geometry of you obviously change notes by changing sounds. You change notes by changing the geometry of the cavities within it, right? By pushing buttons and changing the boundary conditions at different points along that tube. So that's how different notes are created, which is pretty interesting. I don't know how many of you are music people. Everyone, I think, is in some way fundamentally a music person. If you're not, yeah, give it a try. You will find something you like, and you will be. So I wanted to talk about that before we got to our last big topic well, beats is like the smallest topic. So beats, you can look at beat frequencies, which relate to music, and then we get, then we get to the Doppler effect. So beats occur when two waves are very close in frequency. There's a slight difference in frequency, and then you get these beat frequencies. Where you would see this a lot is if you've ever tuned a guitar or tuned a string instrument, which is different than what we were just talking about, which would be brass or wood instruments. But string instruments depend on the resonant frequency of the string that's vibrating. So often when a string is out of tune, you play it with a tuned string, a reference frequency, and then you adjust it. You can adjust the frequency slightly until the beat frequency goes away. And when the beat frequency goes away, you get a nice superposition, everything's in phase, and everything sounds nice in tune. But otherwise, you get this little beat. You hear this little beating that when you're out of tune, when you're doing the frequency adjustments. So now I want to talk about the Doppler effect. So the Doppler effect is one of these huge ideas in physics that is very far-reaching. So we use the Doppler effect to characterize motion fairly frequently, and from everything from police cars that move back and forth all the way out to figuring out the size of the universe. So the Doppler effect plays a critical role in that as well. And as you can see here, we have to, in the beginning of the lecture, if you recall, I told you that those words detector and source would become very important. So here we see that where we have the velocity of the detector and the velocity of the source. Now what you see in front of you here can look very confusing, but it's a very generalized Doppler shift, all right? And it represents sources moving away and from the, so if you have a source and a detector, I'll use my remote control. So there, you'll notice there's a total of 4 scenarios. You can have the detector, or no, the source, we'll call the pen the source and the clicker here the detector. So the source can either move towards the detector or away from the detector, right? Towards the detector or away from the detector. And also, conversely, the detector can move away from the source and it can move towards the source. And now if we have some complex system, we just have to ask ourselves, what am I moving towards, the detector or the source? Or am I moving towards or away from the detector, right? Am I moving, and then you have to do the same thing with the source. This can get a little hard sometimes to decipher. We do have an example problem we're going to do, but in understanding the Doppler effect, I think it makes sense when figuring out which one of these to choose to ask yourself which one increases the wavefronts, right? And I want to do that through the example we have with a bat, but I think it'll be easier to see before we get to bats. It might be easier to see here, where you'll notice you have a source and the ear is your detector, right? So in this sense, the detector is moving towards the source. So as the detector moves towards the source, right, are you going to encounter more wavefronts or less wavefronts than if you just stayed still?
More.
What do you think?
More.
So you're going to get more wavefronts, right? So when you get more wavefronts, you should see that will lead to an increasing term in that Doppler formula, right? So when you have the source, so if you're moving away, you can pick your plus and minus, because you know, first of all, when you look here at this particular situation, you're going to find that, okay, so the source has a 0 velocity, right? So I just have a V on the bottom. I don't have to worry about plus and minus. But if the detector, if it has more, and we're moving towards it, you want to maximize the numerator here, right? So you're going to pick plus, because that'll make it bigger. When the detector is moving away from the source, you're going to get less wavefronts, right? And then you have to get, and then you want to minimize that to represent less wavefronts, and then you'll make the denominator smaller. I don't think I understand your question, Gabriel, about can you use the course? I'm not sure in the chat. But anyhow, I'll wait for a response there. So you can see similarly, right, when the source is moving, but the detector is stationary, right, we can go back here. And now, looking at that second one, we can set this one equal to 0. But you'll notice if the case is that you get more wavefronts, you want to make the number bigger. And you do that by making it smaller in the denominator, right? 1 over a smaller number ends up with a bigger number. So then you choose the minus sign. And then, you know, to make it smaller, the opposite case would be the plus sign. And you can see that, right? If the source moves towards the detector, right, the detector is experiencing more wavelengths, right? It'll see more wavelengths. So that'll help you pick your signs. I find that asking your question, do I see more wavelengths or less wavelengths, is the easiest way to sort of very simply interpret this. And in fact, my astronomy students usually can decompact the Doppler effect looking at it that way. And I think it's pretty helpful. But that being said, we are going to talk about everyone's favorite animal. Well, it's not necessarily everyone's favorite animal, but it's a pretty cool animal, which are bats. All right, and we'll be able to ask ourselves these questions and construct whatchamacallit, the solutions to this problem. Oh, hold on. Yeah, Mina.
Yeah, sorry, Professor. I feel like I'm annoying you.
No, that's the whole. This is literally my job is to answer your questions. None of you should ever feel bad about that, about asking anything.
Thank you, Professor. On the previous slide, I just want to make sure I understand the graph itself, right? So
Sure.
on the left side says where the source is stationary and the detector moves. So
Right.
So according to that, what am I seeing? I don't feel like I get more. Like when I compare those two, left and right, it depends on the detector, right? If the source moves, then we get more.
Well, again, it's relative motion, Mina. So if you just look at this ear, right? So if this ear is getting it's getting some frequency of wavelengths, right? It's getting some wavelength at every so many wavelengths per second, whatever.
Mm-hmm.
So as you move towards it, right, you're beating them there. They no longer have to cover the same distance, so you're going to get more wavelengths as you go towards it than you would if you just stayed still. And if you run away from them, for instance, right? If you run away, then you're moving faster. Then by the time this wavelength gets here, you're not there anymore, right? So you're running away. So it's still moving faster than you, but by the time to catch up to you, it has to move a farther distance. So you're essentially hearing less wavelengths.
All right. And how about on the right side? I'm trying to interpret the difference between those two.
Between these two?
Yeah. If essentially they depict the same thing, why even have two different pictures? That's what I'm trying to understand.
They don't, because they don't depict the same thing. The results are the same, right? You're resulting, whether the source is moving or the detector is moving, that will lead to you either hearing more wavelengths or less wavelengths from that action, right? But when the source moves, when the detector, but basically, so they're the same results, but in one instance, this source is stationary. Like imagine you're a TV, right? You can move around your house, but your TV is stationary. So that's one part of the Doppler effect, right? And that is only the numerator really here. You can actually have Doppler effects if the velocity of the source is 0, then you just have the V down here, right? This is 0, and you can actually have Doppler shifts with just the detector moving. All right. Now the most common version of the other one or this one on the right-hand side, is now imagine you're sitting in class and you hear a siren, like a police car go by, or a fire truck, or an ambulance, and you hear the sirens. And you can actually, if you think about this, you'll probably remember that as it comes closer to you, it sounds one way, and as it goes farther away from you, it sounds different, right? That is the Doppler effect. And so from there, your source, you're just a stationary source sitting there, or your stationary detector sitting there, but the source is moving towards you. So they're physically different, and you can see in your Doppler effect formula here that in this case, the detector's velocity is 0, and now you just have v in the numerator, but now you have to do stuff make considerations in the denominator, right? And then you'll pick your signs based on whether you have more wavefronts or less wavefronts.
Professor, I have a question.
Yeah.
So that means like moving toward that detector or either object, I mean the source, right? It takes positive, right? Toward the, when we go to like when detector go toward the source, right? It's positive, right? It's not negative, right?
Well, when the detective, again, I would encourage you to read it, but I always ask myself the question, am I getting more wavefronts or less wavefronts, right?
Oh,
so
okay.
You asked when the detector's moving towards the source. Is that what you want? Which one you want to know?
Yes.
So if the detector's moving towards the source, you're going to increase your wavefront number, right?
Yes.
So if you're increasing your wavefront, and the detector's moving, so it has velocity. Let's go back to the formula. So if that's true, if you're expecting an increase in wavefronts, that means you want to, this is the part that deals with the detector, right? So that means if more wavefronts means the numerator should be bigger.
Okay.
Right? So then if it's bigger, then you pick plus.
Okay, got it.
That's how I think about it. So I never know how to answer that question, like is it plus or minus? I always ask myself, am I increasing or decreasing wavelengths?
Yeah.
Because I just find that helps.
That's a simple logic. Thank you.
Yeah. Okay, no problem. So we ready for bats? All right, let's do bats. So bats navigate and search out prey by emitting and then detecting reflections of ultrasonic waves, which are sound waves with frequencies greater than can be heard by a human. So we want to suppose, so if you saw Finding Dory, it's similar to the orca's echolocation skills. Love that movie. So suppose a bat emits ultrasound frequency at 82.52 kilohertz, which you can verify is past the human range of hearing, while flying with a velocity of 9 meters per second in some x direction. It's chasing a moth that flies with a velocity of 8 meters per second. So what frequency does the moth detect, and what frequency does the bat detect returning echo from the moth? So this is sort of a two-part problem. And we also have to ask ourselves what's implied with the problem. So the first thing I'd want to do in solving this is I'd want to do my generalized Doppler effect, right? So f prime, or this f0 is the original frequency, right? So that's the bat emits, BE, that's this guy here, right? And then that's going to be equal to V. Oh no, wait a minute, that's me just being silly. So it's going to be F naught times V plus minus V detector over V plus minus V source. So we have to identify what's the source and what's the detector. So when we ask ourselves about the moth here, in this case, is the detector, right? Because we ask what does the moth detect? The bat's the source. So first of all, what quantities are implied here in the problem? So we know that in our first problem, we're just answering here, right? up to here, we can say that VD, the detector, is going to be equal to the moth, right? And that's going to equal 8.0 meters per second. Okay? And the whatchamacallit, hold on. And the bat is the source, right? So we have VBAT equals 9, we said? Or no, VBAT equals V source equals 90 meters per second. My only issue with this program is that deleting things is not quite clean. Okay, so now I asked you what quantities are implied in this problem. So what's going to be in this Doppler shift? What is going to be this V? So this V represents the speed of the wave in the medium, right? Well, what kind of wave do we have here, fundamentally?
Sound wave?
Sound wave?
It's a sound wave. So we know that if it's a sound wave, ultrasound just means we can't hear it. So, but if it's still a sound wave, it still travels in air at 343 meters per second. So we still have that V is 343. Good. Okay, I'll put the units on it. Okay, and now we want to ask ourselves, how are we going to, so now we have our V's, we have our F naught, which is FBE, so we have, I'll write that here, F naught equals FBE, and now we have to visualize this problem so that we can pick the right signage. All right, so now let's take a look at our bat and our moth flying. Okay, so we can only look at one thing at a time. So let's go at the top and look at the detector, right? The moth. So the moth, is the moth flying towards the bat or away from the bat?
Away from the bat.
Away.
Away from the bat. The bat will inevitably catch up, but it's moving away. So will that be more wave fronts or less wave fronts if it's moving away?
More away from.
Yes.
Less wave fronts, right? As you move away from a source, it takes longer for the signal to catch up to you, right? So it'll be less wave fronts. Does that make sense?
Okay.
All right. So in that sense, we have minus, so we can say that F equals F naught V minus V detector. And now we have to figure out which one it's going to be V source, okay? So now the bat, is the bat moving towards or away from the detector, from the moth?
Towards.
Towards, right? The bat is moving towards the moth. So in that sense, get more wave fronts or less wave fronts?
More wavelengths.
More wave fronts. But, and this is the trick, in order to so that you want to maximize the denominator. So in order to maximize the denominator, you want to make it as small as possible, which means
Should be positive.
getting rid of the plus sign.
Oh,
Hold on. Right? So now we have our equation. So as you can see, the work really there is setting up the correct equation. All right? Yeah, Mina.
Sorry, Professor, just for the sake of words.
Sure.
We want to maximize not the denominator, but the fraction. That's why it will decrease the denominator as much as possible, right?
Well, so I want to stop you there. You can't really maximize the fraction. You can only you have to figure out whether you need to maximize or minimize the numerator, and then you can figure out whether you need to maximize or minimize the denominator. The fraction is then just what's resulted from that. So doesn't make sense to maximize one or the, both at the same time. You really have to handle it sort of case by case.
Gotcha. All right, thank you.
By each. So the denominator minus how. So think of it this way, right? If let's look at a few values here. So if I'm considering, we'll do this color off to the side. We'll do this in black. So consider the function y equals 1 over x. All right, and let's plug in some number. Let's look at what happens. Is n, if you have a plus down there, then that means it's getting bigger, right? And as x approaches infinity, right, y goes to 0, right? So 1 over 10 is 0.1, and then 1 over 100 is 0.01, right? And that's greater than 1 over 1,000. That's 0.001. You see how it goes? Right. So when we want to, so when we are, I guess maybe Mina, maybe you are right there as far as maximizing, because the fraction, because you want to maximize the frequency, right? So okay, I see what you're saying now. All right. I just got a little tongue-tied with the words, which is okay. It happens. So right. So you want to maximize the. No. That's fine. I look, being wrong is part of the game, or clearing up misunderstandings is what we do. So when you minimize the denominator here, when you make the denominator smaller, that will lead to a larger value here. Okay, so more wavefronts means higher frequency. So what do you have to do to the denominator to get a higher frequency? Now I get what you mean by maximize and minimize the fraction. Okay, all right, I'm on the same page with you now. But I still maintain that you have to handle it one at a time, right? You have to decide whether the numerator is going to make it bigger or the denominator is going to make it bigger, and then you can figure out what the final result is.
Yes, totally agree on that.
So Professor,
All right.
still right, I'm talking in two kind of like arguments, right? So you are telling me like the denominator is negative, but why? I'm just trying to understand that. That's the specific thing.
So the denominator is negative, right? Because we already determined. So the denominator is the source, right? That the source function is in the denominator. So the source is the bat. So the bat is moving towards the moth.
Yep.
So if it's moving toward it, that'll see an increase in wavelengths, right? It'll see an increase in frequency. So you have to pick the sign in the denominator that will lead to an increase in frequency. Okay?
Increase in frequency.
So and that happens when you make it smaller. When you subtract that 343, when you subtract a little bit off, that makes it smaller and thus makes the frequency bigger.
Okay, got it.
Okay.
Right now. Thank you.
You're welcome. So, so good. Right. So you can see here in sort of a nicer version, they do that, and you get, you'll see we pick the signs right, and then they plug everything in, and you'll notice it's a small increase in frequency, right? So and that makes sense because ultimately the bat is moving faster than the moth. So now to look at the return signal, I want to go back and look at part B. All right, we'll keep this up so that it's written clearly. But now in part B, it wants to know what frequency does the bat detect in the returning echo from the moth. So now they've switched roles. So now in this set in part B, the bat is the detector and the moth is now the source. All right, and you have to use your answer from part A. What do you have to? Right, because the hold on, wait a minute. Let me think through that really quick. So in the echo, let me direction of echo by the bat. So in the echo back to the bat, okay, the moth acts as the source of the second of the, or as the source of the sound, emitting the frequency we just calculated. All right. So now the moth is the source moving away, and the bat is the detector moving forward. So now what I want you guys to try and do, and give your, try and work on it for a couple minutes, is, yeah, and the 82.8, we got it right there. I want you to try and set up the equivalent version here, and see if you can do it on your own for a couple minutes, and then I'll go through it. Okay, so I'm going to give you about 3 or 4 minutes to just give it a shot, and then I'll go through it. When you hear me say stuff like this when you're watching the videos on YouTube, it's a good idea to just pause and work on it until you get frustrated, and then watch me go through it, or fast forward that. There's a lot of, I know the videos seem long, but I forgot to mention that. A lot of breaks are recorded in there, and a lot of pauses for working through problems are in there. So they're not really as long as they look. I'll tell you that. In fact, you know what I'm going to do to get it a little more lively in here, talking about it? I'm going to put you into the breakout rooms so you can work on it together, and I'm not necessarily I'm not necessarily in your ways. So I'm going to break you into 5 random groups, and you'll be able to talk to each other about it, and I won't be in each group at the same time, and the group out thing, your discussions will not be recorded. So I'll send them in so you can discuss it and see what you come up with, and then I'll let you come back and report.